Hi, my name is Austin Wagner, and I'm just here to talk about the library that I made from scratch called ClearGBM, or Gradient Boosting Machine. What ClearGBM is, it's a model that can be used by other training harnesses on tabular data. So any kind of data table, it can be used to look at patterns within the data itself and be used to make a prediction and find which column headers or which features are the most important overall and how they most contribute to the overall outcome of the data itself. In this instance, I trained the models on a US bankruptcy dataset. If we scroll up here on our terminal, we can see that it has 18 features to start. However, as we do this feature optimization where we multiply different column headers by each other or divide them by each other or just take a log or different ratios, we can actually go up to as many as 500 features, which means we're really extrapolating out the patterns from this data from just 18 up to 495. And so that is one thing I did here when I ran the ClearGBM model. Now, I want to kind of start with what is a GBM, gradient boosted machine? And what it really starts as is a decision tree that's just kind of looking at the data and it's picking a value. And it's like if this person has this much income, then their loan is healthy. If this person has a low debt ceiling, then they may also be healthy. And by looking at these columns one at a time, and then also by looking at the ratio and the relationships between these columns, we're able to form what's called a prediction based on this, known as AUC. And this AUC, it differs from straight accuracy. Now, one thing to consider is that if you're using a database that has primarily healthy loans, in this instance, our data is all about loans and whether people are expected to default on those loans or whether they're expected to pay off those loans and complete them. And that's called a covenant breach or the loan health overall. And so, as we're looking at this, we're training these models on these features. We're training LightGBM, ClearGBM, or XGBoost. And so it's coming up with what's called a decision tree, right? It's looking at all these different columns and it's kind of trying to find out, okay, if I follow these specific traits and if I look for customers who have loans with a certain level of income and a certain level of debt ratio, then can we determine yes or no, are they going to default? Now, this differs just from the straight accuracy. If you're looking at accuracy in a data set, but you only have 4% of the data being actual loan breaches or people who defaulted on their loans, then the model could just guess that people would not default. It could just be like everyone, 95, 96% of the time, people are just going to succeed. And so when we use this AUC, what we're really looking at is, okay, how much can the model predict the actual correctness of an individual in this? Not just any one person in the data, but if we look at each individual person that's classified in this data set, how often can it get that prediction for each person right? Right, so it's going through each and every single customer and making a prediction on each and every single feature actually in order to come up with these predictions. So it's looking at all these different columns. And so I implemented what is called this decision tree based on the XGBoost and based on the LightGBM, which are some other existing models. Now, one of the main things you may notice is that as I ran this model, right, my ClearGBM full Python, it does not use any Numpy, which means all the calculations are prohibitively expensive, and they take a very long time to compute. I even did batch feature aggregation in order to handle the features all at once, which did speed it up actually significantly. I also implemented multi-threading, but without that raw C code to really speed it up that you have with NumPy, we're a little bit limited on time. However, we are not limited by our overall predictive accuracy for each individual. right? You can see here we're achieving 0.87, which is comparable to LightGBM, the pre-existing model that does use the C code, right? And it does even better than another existing XGBoost, which is another tabular model, a model trained on tables. And so I was able to make this ClearGBM, this model, using the decision trees and looking at the overall gradients between these different decisions to really find and determine what columns matter, what features matter, and to come up with an accurate predictive model that actually significantly outperformed the existing XGBoost model. Now, this is something that we did from scratch with just Python. I did it in a few days over, with a lot of hours, a lot of time, and a lot of trial and error. But I was able to get something that was comparable to the existing models and could be trained on tables of data in order to come up with nice predictive values and predictive accurate decisions with a nice interpretable layer. And that's ClearGBM, and my name is Austin Wagner.